Hello everyone, my name is Pranay Kapoor and I'm honored to present our paper Silver Surfers on the Tech Wave Privacy Analysis of Android Apps for Elderly Users. This work is a collaboration with my co-author Rohan Page, Professor Mohammad Manan and Professor Ahmad Yusuf. So first and foremost, I would like to shed a light on the elderly population in the world right now. By 2050, there will be an estimated 1.5 billion elderly people in the world. But this population is increasingly adopting new technologies, as 46% of elderly internet users are on a social network, and 27% of all elderly users use at least one social network. But this has hence led to more crimes against the elderly too, as cyber crimes in the US have increased 5 times since 2014 against the elderly people, costing around $650 million yearly. One such example is the grandparent scam, where people lost 328 million, where elderly were hit the hardest. And also the nature of elderly people is that they are trustful, unsuspecting, not well or dependent, which makes them have a higher risk of security and privacy breach. There has been very less research done in this field. Slane et al. Collected seniors' perspective on technological devices and applications to show how seniors protect their personal information. Another group of researchers identified a range of privacy and security needs specific to the elderly. They showed how the elderly have a limited technical knowledge, experience, and declining abilities, which amplify them to have higher risk of vulnerabilities. Also, another group showed that older women were the most vulnerable in phishing attacks in a study of internet users. But as we can see, there has been no comprehensive privacy and security analysis on Android applications and IoT devices for elderly people. So the goal of our research was to perform privacy and security analysis on Android apps used mainly by the elderly, as these apps are one of the main gateways through which an attacker can exploit the elderly population. To do this, we aim to look at the risky PI leakage from apps, look for improper authentication management, find improper access control issues, and improper input validation issues, and to check for third-party library permissions and trackers, and to check for any backend vulnerabilities. For our threat model, we consider three types of attackers. The first type would be an on-device attacker, where the attacker will have a malicious application with limited permissions be installed on the user's phone to help exploit the vulnerable elderly app. Second type would be an on-path attacker, who is placed in between the user's smartphone and its server. This attacker can eavesdrop, modify, and behave like a man-in-the-middle attacker. Finally, a remote attacker would be any attacker who can connect to the app's backend server or exploit the application by being located away from the user and not in his network path. And this attacker would be the most dangerous out of the three too. Also, we do not consider attacks which require physical access of the device, as we believe that it would make a very strong threat model. We now move on to the methodology we used for our analysis. We performed two types of analysis: dynamic analysis and static analysis. So for our dynamic analysis, we first install the application and run it through a proxy. For us, we use Burp Suite proxy, as it allows us full control of the traffic along with just being able to view the traffic as well. We first just view the traffic and identify the domains and trackers for the app. We then differentiate the requests with weak authentication, as they are more likely to be exploitable. We pass these requests through Burp components to check for security and privacy issues. The requests transmitted in GraphQL are analyzed using GraphIQL. We use this dynamic analysis to find improper access control, authentication secret, or input validation issues. It also helps us obtain PII leakage through the network to various domains and third-party trackers. We also look for any suspicious in-app behavior. In our static analysis, we check for the dangerous app permissions using MobSF. We check the third-party libraries using a tool called LightRadar, and we do this to check for the dangerous permissions the libraries ask, and also if the developers use any known tracking or malicious third-party libraries. We check for the Firebase backend vulnerabilities using MobSF again, and it also provides us with the exposed Firebase URLs too. Now on to the results. Due to time constraints, we will only mention the main issues we found, but we encourage you to check out our full paper for the detailed results. In our notable findings, we found a total of 95 out of 146 apps that failed to adequately protect the security and privacy of the elderly users due to one or more issues which are mentioned earlier. 15 apps allow the attacker to easily compromise the account of elderly users, leading to full account takeover. 16 apps transmit sensitive PII via HTTP to their servers, and 8 apps transmit sensitive PII to third-party domains. 9 apps have improper input validation with injection attack vulnerabilities, and we were also assigned a CVE in one app. 4 apps do not properly authenticate their server API endpoints, and 122 unique third-party libraries and a total of over 1000 libraries were found in just 127 of our 146 apps. So we had 15 apps that have authentication management issues. These are by two main types. In the first type, apps like EmpowerG and EZCare have login credentials sent in plain text over HTTP. So any on-path attacker who is sniffing the traffic will be able to get the username and passwords to log into the apps and perform full account takeover. In the second type, apps like Allwell Senior Care and Seniority, we can perform an OTP brute force attack to get a full account takeover by a remote attacker who knows the registered phone number. This is possible as these apps do not implement any rate limiting in their request and their OTPs are less than or equal to 4 numerical digits. We had 10 apps where the session IDs were sent in plain text over HTTP. For example, POC EVV had this issue, so any on-path attacker can replay a request from this app and perform an account takeover. Also, 8 apps do not use any authentication secret at all. This may not be an issue in isolation, but it can lead to other severe issues. For example, in Golden app, it did not have any authentication secret, which led to improper access control issue. This is because the app's authentication mechanism is purely based on the user's mobile number. So an on-path attacker can change the mobile number in the requests and log into the replaced numbers account. This leads to identity theft of the user. We had 4 apps with improper access control. As mentioned earlier, in Golden app we can perform identity theft of the user. In POC EVV, a 5-digit parameter as the user ID is present in the requests, which can be changed to get the other user's data on the platform by a remote attacker. This data includes the phone number, the home address, the office address, and so on. Damawa also has a similar issue which can lead to a full account takeover. This is because the appointment details section in the application do not implement any access control. So an attacker can fetch the user data using GraphQL query and modify the user ID. So the attacker can view, modify, and cancel any elderly patient's appointments. 9 apps are vulnerable to various injection attacks. Apps like EmpowerG and Tricella Health had APIs which were vulnerable to SQL injection. For ethical reasons, we cannot test the full extent of these vulnerabilities and only check till the point where we can confirm that these vulnerabilities exist. So to check for SQL injection, we added an SQL query in the intercepted request which contacted a domain which was under our control. If we saw the domain being contacted, we confirmed that the SQL query was being executed. Apps like Eligrid and Seniority are vulnerable to code injection. Similar to the previous issue, we cannot test the full extent of this attack, but a remote attacker can construct and send modified requests to the app's server. To verify this issue, we compare the delay time between responses after we add a JavaScript time delay function in their respective requests. Now moving on to the data being leaked by the apps via the network traffic. 128 out of the 146 apps communicate with 478 third-party domains and trackers. 16 apps send PII in plain text over HTTP. This includes PII like username and password, mobile number, home addresses, and even the exact geolocation in some cases. These types of information are highly sensitive, which leads to severe privacy concerns. 18 apps also send device information like phone bill, model number, and so on. And this may not seem harmful at first, but it is used in the reconnaissance stage of any attack. The top two trackers include Crashlytics, which is used for app maintenance in case of any app crashes, and DoubleClick, which is a marketing tracker which offers user analytics to companies. In the static analysis of the third-party libraries, we found 122 unique third-party libraries and a total of just over 1,000 libraries in only 127 of our apps. Caregiver and EVV apps had the most number of libraries. The three types of permissions which were asked were the dump permission, write secure settings permission, and write APN settings permission. For example, the write secure settings permission is a development aid library permission which should only be seen in Android system applications as it allows the applications to read and write to the secure system settings. To provide a more holistic view from each app's perspective, we would like to show two case studies. These two apps are Eligrid and Tracella Healthcare. Both of these are companion apps for their smart pill organizers, which are specifically designed to help the elderly by reminding them to take their pills on time. So first of all, Eligrid. We were assigned a CVE for the code injection vulnerability which we mentioned earlier with a CVSS score of 9.8 out of 10, which shows how critical this vulnerability is. An attacker can also enumerate a caregiver's user ID by brute force in the requests and then supply to modify the caregiver's email and will give the control of the pill alerts to the attacker. So all of the medications can be tracked or the amount of times the user takes the medication can be tampered with. On the other hand, an attacker or the user can upgrade to the premium plan for free, as there is a Boolean parameter in the user profile API which can be changed. For Tracella Healthcare, we can perform a full account takeover by brute forcing the 3-digit OTP. And after that is done, the remote attacker can do anything he wants. He can change the medication, skip the medication, or increase the medication at his will. And as we know how precise every medication needs to be for the elderly people, this can be extremely fatal for them. This app also has SQL injection issue, which also makes other users on the server vulnerable. So in conclusion, first to recap, in total 95 out of 146 elderly apps have one or more privacy and security issue. We hope that our work doesn't stop here, as we believe that there is still a lot that needs to be done. For example, researchers can test elderly apps from other app markets like the Chinese app market, and also test some iOS apps, as we only test in the Android app market. We also think that there needs to be strict policies and regulations for this demographic, as there is COPPA for children and HIPAA in the US for health information. So we think that there can be some regulations for the elderly people too. Also, many issues we found can be mitigated if developers just follow the basic security best practices. So if there is more awareness on that, then all of our apps will be more safe. Thank you for listening our presentation, and please feel free to ask us any questions.
Hi, I'm Robert from the Network and Information Security Group at Tampere University in Finland, and I'm gonna present the paper we wrote called MetaPriv, Acting in Favor of Privacy on Social Media Platforms. So, in this presentation, we're going to discuss privacy problems on Facebook, existing privacy tools, our proposed tool, and how we can measure privacy on Facebook, and finally our implementation and results. Social media platforms like Facebook make money mainly from ads. For users to see ads, they need to make them engaged into their platform, which is mainly done by showing the users what they want to see based on their preferences. This leads to people receiving biased information because they only receive information that affirms their already established opinions. Then, when the user is engaged and the algorithms learned everything about the user, Facebook will start showing targeted advertisements, and sometimes they can feel a bit too accurate. With regards to privacy from the social network, most users seem to be left with two options: either regular use of the platform, so you have no privacy, or complete abstinence from the platform, so you have full privacy. However, this can be problematic since the option to fully remove all your data from Facebook can be hidden quite deep in the profile settings. Then also Facebook can track you even on different websites through a thing called Facebook Pixel, which is essentially a web element that a lot of companies add to their website to let users share and like articles easier. Finally, and probably most importantly, it's quite inconvenient for many people to delete and not use Facebook, since they want to keep in touch with their friends, keep up with the news, or maybe their job even requires them to use Facebook. So most users would probably prefer to get something like a balance between privacy and convenience rather than complete abstinence. And this became the main motivation for our work. When we look at tools for achieving this goal, well, we don't see much. For Facebook, there are some tools like FaceCloak. This tool hides data such as age, name, and email from Facebook and stores it on an encrypted server. Then the other tool is Scramble, which allows users to enforce access control over the data. But the problem with these tools is that they don't take into consideration other interactions with Facebook. Interactions like, for example, likes, video watches, comments, searches, and so on. We think that these interactions are more important when it comes to privacy from the social network. The other thing is that these tools are about 10 to 11 years old, and their implementation doesn't really work on modern browsers. For Google, however, there are at least some tools. For example, there's Ad Nauseam. It's like an ad blocker, but it doesn't just block the ads, it also clicks on them. And by doing this, it manages to diminish the value of real ad clicks. So essentially, Google learns incorrectly about your interests. Another more recent tool is Harpo, which uses reinforcement learning to adaptively visit random pages. So it doesn't just click on everything, but does it in a more user-like fashion. Now these two, they don't really focus on Facebook, but they served as a main inspiration for our work. And thus MetaPriv was born. And its main idea is that since the social network personalizes users by analyzing their activities on the platform, to achieve privacy, the sole action required is to generate noise traffic on behalf of a user. Or in short, if they want data, let's just give them a lot of random data. So, in our initial design, we have the user, which with his profile and different interests, and we have a bot, and this bot would simulate user interaction. So this bot gets the credentials and a set of keywords from the user, and then it logs into Facebook. Then it searches for pages related to the keywords, saves these pages in a local database, and goes to one page from this database and starts liking some posts from this page. Then it waits for some time, goes to a different page and does the same thing. This is essentially done in an infinite loop, and the waiting is done so that you wouldn't generate too much traffic, which could lead to Facebook stopping you for some time. So by doing these steps, you manage to add noise to your account, to your personal account, and consequently, you manage to frustrate the social network, Facebook. Now, using this design, we ran experiments and saw that we didn't get as much noise as we wanted, so we decided to extend its functionality. Now, in our final version of the tool includes video watching instead of just waiting. Then it also includes suspending and resuming when the PC goes to and from sleep. And finally, it auto-generates keywords from a seed keyword. And these auto-generated keywords, they are also related to the initial seed keyword. These extensions make the tool more user-friendly, they add more variety to the noise, and they make the tool work in a more user-like fashion. Next, we need to test our tool. However, in order to do that, we need some sort of metric that would tell us if it works or if it doesn't work. Thus, we've thought of calculating privacy with the following formulas. So essentially what these formulas do is they take the average amount of real traffic that Facebook presents you in its feeds, and then it subtracts the average amount of noise traffic presented in these feeds. The feeds we considered are the main feed, the suggested posts from the main feed, the main video feed, and the latest video feed. After we do the subtraction, we get a privacy value, and this privacy value can be between -1 and 1. And essentially, the smaller that value is, the more privacy you get. So if it's around 0 or less than 0, that means that there is more noise in your feed than real stuff. And therefore, in this case, we say that your account has become private. Now, with this in mind, we proceeded to run experiments with the tool. Mainly, we ran the tool on a newly created dummy account and on 2 accounts that existed for a few years. On the dummy account, we ran the tool for 10 weeks, and we used only the basic version of the tool, so no video watching. Also, on the dummy account, we simulated both the noise interaction and the real interaction with the tool. Then on the real account, we ran the tool for 4 weeks, and we ran it with the basic and also with the extended version of the tool. So after running on the dummy account, for the first 2 weeks, we built the real interests of the user, and then we proceeded to gradually add more noise each week. So on week 6, the amount of noise we were generating was equal to the amount of real traffic we were generating. And after we analyzed the different Facebook feeds, we saw that these feeds followed a similar trend. So as we can see on week 6, the privacy value is close to 0, which means that the real traffic is almost, the amount of real traffic is almost identical to the amount of noise traffic. So in essence, we conclude from this that users can achieve privacy once the noise traffic is equal to the real traffic they generate. Then we proceeded to add more noise the following weeks, and we wanted to see how the feeds would behave under different circumstances. For example, on weeks 7 to 8, we were generating only noise traffic, but we still saw stuff related to real interests in the feeds. Then on week 9, we started reinforcing the real interests again, and we started seeing more real interest related feed. Then on the real accounts, we analyzed the feeds only after 4 weeks of running the tool continually. In this case, however, the tool interacted with Facebook much more than the user actually did. However, it still took a while to achieve a privacy value close to 0. Then we see that the account on the left has more noise in the main feed as compared to the account on the right. And most of the noise is from suggested posts. Our theory here is that the account on the left had more keywords that were of interest to Facebook. So this means that basically if users like traffic related to related to these keywords on Facebook, then Facebook can show them more ads that would make them more money. Then we also see that the account on the right has significantly more noise feed that is in the latest video feed. We believe that this is because the account on the right had keywords such as cooking, chef, and kitchen. So traffic related to these keywords would generate feed like cooking recipes, and most cooking recipes would probably be in videos, in a video format. So with these observations in mind, we conclude that adding noise efficiently depends more on the keywords themselves than on the amount of likes and video watches. But nevertheless, after calculating the privacy values, we get 0.06 for the account on the left and 0.13 for the account on the right. The account on the left basically managed to have its noise traffic almost, its noise feed almost indistinguishable from its real feed. So according to our definition, that means that the account on the left has achieved privacy. The account on the right, however, likely needs more time to run the tool. For future works, we would like to do more experiments with hot topics and see how much the keywords themselves influence the Facebook feeds. Then we would like to develop a denoiser that would filter the noise posts from Facebook feeds when the user wishes to view his feed. And finally, we would like to find a way to simulate a larger number of users and then run the tool and then see how running the tool would affect their privacy. So, as a summary, we built a tool that adds new privacy safeguards for social network users, can strike a balance between privacy and functionality, and from the experiments we proved that it works, and we saw that results might depend on keywords and on current hot topics. Thank you, and questions.
Hello everyone, I'm Xiaoting. Today I'm very happy to present our work, Adversary for Social Good, leveraging Attribute-Obfuscating attack to protect the social network's user privacy. I am a staff research scientist from Visa Research. This work is collaborated with Lin-Wei Chen from Wright State University and Dinghao Wu from Penn State University. In this big data era, social media becomes indispensable in people's daily life. They attract a lot of research studies to learn our communities and individuals. The social network in social media is naturally represented as graph-structured data, which contains individual activities and complicated relationships. As shown in the slide's figure, nodes in these social graphs usually encode a user's information with respect to their profiles, posts, or photos, while the graph edges connected users with their friendships, kinships, or follower-followee relationships. With the development of deep graph learning, graph neural networks provide powerful techniques for graph understanding and mining. These GNNs take the connectivity structure of the graphs, which we call them adjacency metrics, to perform neighborhood information aggregation to extract high-level features from the nodes and their neighborhoods. And they have boosted the state-of-the-art for a variety of downstream tasks. Those rich for information and powerful tools not only benefit the researchers, but also the attackers to deploy attacks to disclose users' sensitive information and fulfill their malicious intents. Among these attacks, we focus on inference attacks in particular. An inference attack aims to infer private data of an individual, a software, or a system with their by leveraging GM classifiers to automatically analyze their public data. As illustrated in the figure, we have public content on social media, such as user tweets, blogs, and then we borrow GM models to conduct the inference attack to infer users' sensitive information. Such attacks pose serious threat to our people's privacy, and valid protection methods are needed. Let's take a look at the focusing our work. The GM-based inference attack can be demonstrated in the example here. The inference attackers are equipped with powerful GM models and use the rich for public data, including user features, graph structures, and labeled attributes to automatically infer users' personal attributes such as age, gender, location, career, and the political views that people are unwilling to disclose on social networks. Despite the great success, GNs are found to have such learning security challenge of lacking adversarial robustness, which are found in many regular machine learning models. And a recent research trend is an adversarial graph that accounts for poisoning attacks launched towards original graphs. Like the example here, by performing small perturbations on graph structures or node features during the training, the well-trained model can be fooled into misclassification. Based on such observation, our research question becomes, can we leverage such vulnerability of GN models to against the GN inference attacks? And the research goal in this work is to take advantage of the vulnerability of GN models and protect the user's attribute privacy from a novel adversarial learning perspective. To achieve such goal, we have the following challenges. As inference attackers have a variety of choices in GN constructions, it is impossible for us to assess the inference models for crafting graph adversarial attacks. Also, modifications on graph structures or user features are not that practical in our cases because of two reasons. First, in social media context, user nodes usually encode multimodal data, such as profiles and posts, where the perturbations computed from the feature space are hard to map to the user's information space in an end-to-end manner. Second, due to the limited access to large-scale social networks, it is unreasonable for us to assume that we can alter any relationship as we want. To resolve these challenges, we propose a black box adversarial poisoning attack called Attribute-Obf by manipulating the training attributes. Under the black box setting, we train our own surrogate model to imitate the inference attacker, and we modify the training attributes instead of node features or edges because we think it's necessary for inference attackers to collect those initial attribute annotations for training. While the users annotating on social networks generally relies on their self-reporting. Therefore, Attribute-Obfuscating can be conveniently realized by users and passed to the subsequent inference attacks. And our framework briefly goes like this. Given a social graph data, Attribute-Obf proceeds by modifying a small portion of optimal training users' attribute values, while the obfuscated attribute information can propagate along the whole graph through the layer-wise message passing, such that the overall performance of attribute inference by a GN attacker is degraded. In this overview of our framework, the core design is our Attribute-Obf algorithm designed to find the optimal training attributes to modify. In the following slides, I will explain some technical details. In an inference attack, given adjacency matrix, feature matrix, and training attribute values, we can train a GNN model by minimizing the training loss and obtain the optimized weight matrix W. To attack such inference model, we aim to conduct a graph adversary attack by modifying the training data to prevent it from correctly identifying the user's private attributes. Therefore, our training objective goes like this. As we can see from the objective, it is actually a two-step optimization process. First, we train a GN model with the labeled training data and obtain these optimal parameters W star. Second, we want to maximize the prediction error when apply the trained model to those unseen testing data. And here, phi denotes the attribute-obfuscating operation on the training attributes. That is exactly what we want to compute in our optimization. And epsilon is the modification rate on our graph attributes to ensure that our Attribute-Obf is unnoticeable. To solve this objective, we have two challenges. First, like what I mentioned before, this is a challenging bi-level optimization problem where an optimization involves another optimization as constraint, because we want to maximize the test loss after optimizing the model parameters W on the modified graph G. This is a non-convex and intractable problem as the graph parameters are already constrained before we modify the graph. And when we modify the attribute, it would reversely affect the optimized parameters optimized in our prior training step. Second, the training attribute data and the action space of perturbation attributes is discrete. For example, the attribute value y is encoded as the discrete numbers that represent their classes. And when we optimally find the operations on training attributes, the exhaustive search is infeasible. We can turn to the mostly used gradient-based method. However, the obfuscating operation is non-differentiable in this case. To solve the bi-level optimization challenge, we first use a linearized model to approximate the GN model. Specifically, we use a two-layer simple graph convolution model as a surrogate model to perform our attribute-obfuscating attack on social graphs under the black box setting. There is a couple of reasons why we choose it. It not only removes the nonlinearity between model layers, but also captures the idea of graph convolutions. In addition, SGC model has been deployed as a surrogate model in some previous graph adversarial attack formulations. In this regard, the optimal parameters W star after the first step training can be rewrote like the formula showed here. By applying specific loss function, we can approximately get the closed form solution of W star as the following formula, and we use key to represent this part for the sake of simplicity in the following slides. Now we replace the parameter W star in our objective with its solution like this. So our bi-level optimization problem becomes a single level. Next, we need to fix the other challenge we mentioned before, the existing non-differentiable component in the objective. And our solution is to replace the non-differentiable categorical samples with differentiable Gumbel softmax, so we can use backpropagation to compute the gradients and find the optimal operations on the training attributes. Categorical variables are natural choice to represent the discrete structures. The attribute values in our setting are considered as a dimensional matrix, where each row is a one-hot categorical distribution specifying the attribute class. Furtherly, we use the Gumbel softmax function as a continuous differentiable approximation to simulate the original categorical sampling, and replace the non-differentiable component in our objective function. In this Gumbel softmax function, G is a small variable, follows the Gumbel distribution, and P is our attribute categorical distribution. Here I show a simulation example for better understanding. On the left side is our regular one-hot categorical distribution, and on the right are the Gumbel softmax distributions. Tau is the temperature parameter in Gumbel softmax function, and we can see that when tau is close to 0, the Gumbel softmax distribution almost becomes the one-hot distribution. Here comes to our experiments. In our experiment, we evaluate our method on a couple of real-world datasets, and the private attributes of this dataset include binary, politics, career, gender, and the non-binary class year. To be comparable, we follow the training setting in previous work, and the number of annotated nodes is 20 per class. In our experiments, we tested the accuracy of 5 inference settings while using our Attribute-Obf method to modify different rate of training attribute values. In the figure, the lower inference accuracy means our attack is more effective. We show some of the results here, and we can see that our method can intensively decrease the accuracy of inference attacks. It's obvious that the larger portion of training nodes we modify, the lower the attacker's inference accuracy is. We can also find that those multi-class inference attacks are much more difficult to defeat compared to the bi-class inference tasks. In the black box setting, we don't know the attacker's model in real attacking scenarios. This naturally leads us to the question, can our attack strategy generalize to other inference attack models? So in our evaluation, we investigate the transferability of our method. We tested inference results on poisoned data against the full state-of-the-art GN models. The results in the figure demonstrate that Attribute-Obfuscating can promisingly transfer the attacking capability to different GN models. We also found that the complexity of the attack model can affect the transferal results, which is the results on those simple structured models tend to outperform those with more complex structures. Here are some takeaways about this presentation. So in this work, we present a new adversarial poisoning attack, Attribute-Obfuscating, on graph neural networks. We explore from a novel angle to protect social graph data privacy by designing a practical adversarial attack. We have done extensive experiments on public datasets and show the effectiveness of our method on attribute obfuscation. That's all about my presentation. Thank you for your listening. Here are some information about me. My research interests intersect adversarial machine learning, graph learning, and software security. If you are interested in my other work, feel free to check it out. Thank you.